Millions of drivers install cold air intakes, plug-in performance chips, and aftermarket exhaust systems for one reason. They're promised more power, sharper throttle response, better fuel economy, something that wakes the car up. The marketing is confident. The dyno charts look dramatic. The sound clips are convincing. But here's the real question. Are you actually increasing performance? Or are you just increasing noise and spending money? Let's get started. Modification number 1. Cold air intake. The cold air intake is probably the most common first modification. It's affordable, easy to install, and the marketing is aggressive. 10 to 20 horsepower, sharper throttle response, cooler air for denser combustion, even improved fuel economy. On paper, it sounds like free performance. Mechanically, the reality is more restrained. Modern factory intake systems are not crude plastic tubes choking the engine. They are engineered assemblies. They draw air from outside the engine bay, often through fender wells or sealed ducts. They're designed to smooth airflow before it reaches the mass airflow sensor. That smoothing matters, because the ECU depends on accurate airflow readings to meter fuel correctly. Turbulence or uneven airflow can distort those readings. Aftermarket systems often replace a sealed airbox with an exposed cone filter. Unless properly shielded, that filter sits in the engine bay, absorbing radiant heat from the exhaust manifold and radiator. At idle or low speeds, that air can be hotter than what the factory system was drawing. Hotter air is less dense. Less dense air carries less oxygen. Less oxygen means less potential power. Then there's airflow itself. Engines are demand-driven systems. They only pull as much air as the throttle plate opening and cam timing allow. A larger intake tube does not force air into the engine. It reduces restriction slightly. On a naturally aspirated engine that is not intake restricted from the factory, that reduction is often marginal. Dyno results reflect this. On most naturally aspirated engines, gains fall in the 0 to 5 horsepower range, usually at high RPM near redline. In some cases, low-end torque drops because increased tube diameter reduces intake air velocity at lower engine speeds. That can make the car feel softer off the line. On turbocharged engines, the story is slightly different. Reducing intake restriction can help the turbo spool marginally faster. There can be small gains in response. But meaningful power increases usually require ECU recalibration to take advantage of the improved airflow. Without tuning, the gains are modest. It's also important to discuss dyno margin of error. A 10 horsepower gain on a 300 horsepower engine is just over 3%. That is often within normal dyno variation caused by temperature, humidity, or fuel differences. Many advertised gains sit inside that window. There are downsides. Oiled filters can contaminate MAF sensors, leading to incorrect fueling and check engine lights. Some high-flow filters sacrifice filtration efficiency, allowing more fine particles into the engine over time. If airflow readings shift outside expected parameters, the mixture can run lean until fuel trims compensate. And warranty disputes become more complicated when non-factory induction components are installed. Mechanic verdict? For most stock daily drivers, cold air intakes are primarily a sound upgrade. They make the engine louder under throttle. They create the perception of performance. But they rarely deliver transformative, measurable gains. If the intake is subtle, the next modification is not. Modification number 2. Performance chips/ECU tunes. Performance tuning comes in several forms. Plug-in piggyback modules that intercept sensor data, full flash tunes that rewrite ECU software, and the infamous fuel saver resistor chips that alter intake air temperature signals. They all promise dramatic results: 30 to 60 extra horsepower, better fuel economy, plug-and-play transformation. Unlike intakes, tuning can produce real power, but it does so by changing fundamental engine parameters. An ECU tune modifies ignition timing, boost pressure on turbocharged engines, fuel delivery targets, throttle mapping, and sometimes rev limits. Advancing ignition timing and increasing boost both raise cylinder pressure. Higher cylinder pressure generates more force on the piston. More force equals more torque and horsepower, but increased cylinder pressure also increases heat and mechanical stress. On turbocharged engines, gains of 40 to 80 horsepower are realistic with quality tuning. torque increases are often even more dramatic, especially in the mid-range. Turbo engines leave the factory with conservative boost targets to meet emission standards and long-term durability goals. There is usable headroom. Naturally aspirated engines, however, see minimal improvement. Without forced induction, there is limited extra airflow to exploit. Timing adjustments alone cannot produce dramatic gains without pushing toward knock thresholds. The cost of added power is not theoretical. Higher combustion temperatures increase knock sensitivity. Turbochargers spin faster and operate at higher exhaust gas temperatures. Transmission components experience more torque than originally calibrated for. Cooling systems work harder to dissipate additional heat. Potential consequences include accelerated turbo wear, increased spark plug degradation, head gasket stress, and, in high torque applications, transmission slip or clutch wear. Modern engines are durable, but they are not immune to physics. The fuel economy claim also needs clarity. A tuned engine may operate slightly more efficiently under light load if timing is optimized. But when boost and power are used, fuel consumption rises. Most drivers use the added power. That means more fuel burned, not less. Mechanic verdict: a professionally developed tune from a reputable source can deliver real performance gains, especially on turbocharged platforms. But it does so by narrowing the reliability margin the manufacturer built in. Accelerated wear is the trade-off. Cheap plug-in chips that promise miracle gains without altering core calibration logic? Avoid them entirely. Now let's talk about the loudest modification of all. Modification number 3, aftermarket exhaust systems. Exhaust upgrades are the most visible and the most audible modification on this list. They're also the most misunderstood. We need to separate 3 categories clearly: catback systems, downpipes, and full turboback systems. Each does something different mechanically, and the power outcomes vary dramatically depending on engine type. Marketing claims are predictable: 15 to 40 horsepower, better engine breathing, improved fuel economy, and a freer, more aggressive character. The implication is that the factory exhaust is suffocating the engine. Let's unpack the physics. Exhaust systems influence 3 main variables: back pressure, exhaust scavenging, and turbo efficiency on forced induction engines. Reducing restriction allows exhaust gases to exit the combustion chamber more easily. On certain engines, especially older ones, this could unlock meaningful gains. But modern stock exhaust systems are not crude choke points. Manufacturers design them with flow modeling, emissions constraints, and NVH targets in mind. Catalytic converters today are far more efficient and less restrictive than those from the 1990s. In many cases, the stock system is already capable of supporting modest power increases without becoming the primary bottleneck. On naturally aspirated engines, a catback system, meaning everything behind the catalytic converter, typically produces minimal measurable gains. 0 to 5 horsepower is common. The improvement, if any, usually appears near redline, where exhaust flow demand is highest. At low and mid-range RPM, differences are negligible. What changes dramatically is sound. Throttle feels sharper not because torque has increased significantly, but because the auditory feedback is amplified. The engine feels faster because it sounds faster. Real power gains on naturally aspirated platforms usually require a combination of headers, camshaft upgrades, intake improvements, and ECU tuning. An exhaust alone rarely transforms the engine. Turbocharged engines tell a different story. A downpipe, which replaces the restrictive section immediately after the turbocharger, can meaningfully reduce back pressure before the catalytic converter. Lower back pressure improves turbo efficiency. The turbo spools faster, operates at lower exhaust gas temperatures for a given boost level, and can sustain higher flow rates when tuned appropriately. On a turbo engine with proper calibration, a downpipe can deliver noticeable gains. Throttle response improves, mid-range torque increases. Dyno charts show real differences, but there are trade-offs. Many high-flow or catless downpipes violate emissions regulations. They often trigger check engine lights due to oxygen sensor readings outside expected parameters. In regions with strict inspections, they can cause outright failure. Warranty disputes are common, especially if engine or turbo failures occur. Long-term considerations matter too. Louder exhaust systems often introduce cabin drone at cruising speeds. What sounds exciting for the first week can become fatiguing after months of highway driving. O2 sensors may degrade faster due to altered exhaust gas characteristics. And depending on dealer interpretation, powertrain warranty coverage can be questioned. Mechanic verdict? On naturally aspirated engines, aftermarket exhaust systems are primarily sound upgrades. They enhance engagement but rarely deliver substantial standalone power. On turbocharged engines paired with proper tuning, a downpipe or full system can produce legitimate gains. But emissions and reliability implications must be acknowledged. Now let's look at the reliability equation. Let's compare stress levels clearly. A cold air intake introduces minimal additional stress. An exhaust system, unless paired with aggressive tuning, has low to moderate impact. A performance tune, however, is a direct stress multiplier. Power is proportional to cylinder pressure. Increase booster timing and cylinder pressure rises. That pressure loads pistons, rods, bearings, head gaskets, and head bolts. It increases combustion temperature. It accelerates fatigue cycles. Horsepower is easy to add. Longevity is expensive to rebuild. Every performance gain must be viewed through that lens. Here's the financial breakdown. Cold air intake, $300 to $600. Exhaust system, $1,000 to $2,000. Tune, $600 to $1,500. Combined, many owners spend between $2,000 and $3,500 chasing incremental gains. Now consider alternatives. High-performance tires dramatically improve grip, braking distance, and steering response. A quality brake upgrade improves stopping confidence and fade resistance. Suspension upgrades improve cornering stability and ride control. In real-world driving, tires change the character of a vehicle more than a 5-horsepower intake gain ever will. Yet they rarely get the same excitement. So why do people install these modifications? Sound. Immediate sensory feedback. A louder engine feels stronger. Humans equate noise with speed. It's instinctive. There's also community validation. Modification culture thrives on personalization and visible change. Ownership becomes identity. None of that is irrational. Cars are emotional machines, but emotional engagement should not be confused with measurable performance. Here's my final take. Cold air intake, minimal measurable power, primarily sound. Performance tune, real power. Real increase in wear. Accept the trade-off consciously. Exhaust, mostly sound on naturally aspirated engines. Legitimate gains on turbo platforms when paired correctly. If you want reliable daily performance, buy the higher output engine trim from the factory. Manufacturers engineer those components for sustained load. If you want a project, modify intelligently and budget for maintenance. If you want sound, admit it's about sound and enjoy it. Now I want to know, have you installed any of these? Did you measure real gains on a dyno, or did it just feel faster?